Very good morning, all. So, let me introduce for the first time TS diagram. TS diagram. Let me introduce for the first time the TS diagram. Let's see what is TS diagram. So we have already seen PV diagram. Now here the temperature is taken on y-axis and entropy is taken on x-axis, and now we start trying to represent, I repeat, now we start trying to represent our cycles or processes on TS diagram. Okay, no problem at all. Assume a process to be something like this. There is a process something like this. There is a process something like this on TS diagram. Okay. Right. Let us take 2 points. Let us take 2 points which are very close to each other. I repeat, we have taken 2 points which are very, very close to each other. There are 2 points which are very close to each other. You project this, and let this entropy change be some ds. I have taken to, if I take point here and point here, there is a large difference in temperature. From here to here, there is a huge difference. But if I take very close, if I take very, very close to each other, in that small range, if I take very, very close to each other, in that small range, the temperature is assumed to be almost same. I repeat, my dear friends, I have taken 2 points which are very close to each other. I repeat, I have taken 2 points which are very close to each other, and in the small range, the temperature is almost the same. If I take something like this is different, but if I take something like this very small, so in that the change in temperature is very negligible, I can assume almost to be same. Now let us calculate this area. Let us calculate this area. Now just observe here, what is that I have taken? Just observe what is that I have taken. So let us zoom it and see. We have taken, actually let us zoom it and say this curve we have taken, ye wala, this point is this and this point is this, and we have projected and we are calculating this area. Very good, this area. Now this area will be equal to, what is this area? Length into width, length is t, width is ds, so it is t ds. Okay, we have already seen that ds is equal to d dash q by t. It is strictly, yesterday we have seen, it is strictly for reversible. So therefore, reversible process. So d dash q is equal to tds. Now observe here. The right hand side of these two equations, 1 and 2, the right hand side of these two equations is same. When the right hand side is same, definitely the left hand side should be same. Therefore, d dash q is equal to area. What does it mean? It means area under the curve. Listen, which area? There is a curve, under the curve. When you project it on what axis? Entropy axis. You are not projecting on this axis, temperature axis. When the area is projected on entropy axis, under the curve, under this curve, whatever the area is giving, that is nothing but your heat transfer. That is nothing but your heat transfer. That is nothing but your heat transfer. But it should be reversible heat transfer, because this equation is strictly valid for, it is strictly valid for reversible. Therefore, it is valid for reversible. So now I write a golden sentence. The golden sentence is, now I write a golden sentence. The golden sentence is, dekho, concentrate, area under the curve when projected on entropy axis on which diagram? TS diagram gives heat transfer. No, gives no reversible heat transfer. Gives reversible heat transfer. Gives reversible heat transfer. So area under the curve when projected on entropy axis gives reversible heat transfer. Area under the curve when projected on entropy axis gives reversible heat transfer. Reversible heat transfer. It gives reversible heat transfer. Reversible heat transfer. So now please observe clearly on PV diagram. When you are projecting it on volume axis, it gives reversible work transfer, but for a closed system. So PV diagram work, TS diagram heat. I repeat, PV diagram work, TS diagram heat. So now let us try to get used to this TS diagram. I repeat, my dear students, let us try to get used to this TS diagram. Very good. अब देखते हैं. Now let's see. देखते हैं please. Representation of Carnot cycle on TS diagram. Let us represent, I repeat my dear students, let us represent Carnot cycle on TS diagram. Already we have represented Carnot cycle on entropy depends on temperature. Entropy depends on, who said entropy depends only on temperature? There is nothing like that. It has so many parameters. So generally in thermodynamics, look at Biswa Viplav. Generally in thermodynamics, the convention is intensive properties are taken on y-axis, extensive properties are taken on x-axis. That is the general convention we follow in. Yes, I know cause effect, what is the cause, what is the effect, that is taken, but in thermodynamics, the convention generally followed is intensive, independent of mass. So when mass is increasing, property is increasing, therefore we put it on x-axis. When mass is increasing, the property is increasing, therefore we put it on x-axis. Generally that is the convention we follow in thermodynamics. Okay na? Is it okay, Biswa? Dr. Biswa, is it okay? Yes. Now let us represent Carnot cycle on TS diagram. You know that in Carnot cycle there are 4 processes. You know in Carnot cycle there are 4 processes. 1 to 2, 2 to 3, 3 to 4 and 4 to 1. It is okay. In Carnot cycle all processes are reversible. In Carnot cycle all processes are reversible. So therefore reversible isothermal heat supply or expansion. Then reversible adiabatic expansion. Then reversible isothermal heat rejection and already we have seen Carnot cycle. Already I had explained Carnot cycle. I repeat my dear friends. Already I had explained Carnot cycle. There are 4 processes. 2 isothermal, 2 adiabatic, but all are All are reversible. Yesterday we saw some good concepts. Please observe here. Please understand. In a reversible process, there are three things. Heat supply, heat rejection, no heat transfer. Heat supply, heat rejection, no heat transfer. Now, when the heat is supplied, already we have seen entropy increases. When the heat is rejected, entropy decreases. And reversible adiabatic, this is adiabatic, no heat transfer. This is adiabatic, no heat transfer, isentropic. All these I had explained yesterday. In a reversible process, when heat is supplied, entropy increases. In a reversible process, when heat is rejected, entropy decreases. In a reversible process, when there is no heat transfer, it is isentropic. Now let us represent Carnot cycle on TS diagram. यहाँ represent करेंगे. We'll represent here. Listen. Listen, my dear friends. What is 1 to 2? What is 1 to 2? Reversible isothermal heat supply. How do I represent isothermal on TS diagram? On TS diagram, temperature is constant. Temperature is constant. Yes. So on TS diagram, this is isothermal. Temperature is constant. Temperature is constant. Okay. Now, isothermal heat supply. Heat supply. When heat is supplied, you know, isothermal heat supply. When heat is supplied, the entropy is increasing. The entropy is increasing. Therefore, it is 1 to 2. Heat supply. Therefore, it is heat supply. 1 to 2. Reversible isothermal expansion 1 to 2. 1 to 2 is heat supply. 1 to 2. Why are you moving to the right? Why are you moving to the right? Because in heat supply, the entropy increases. In heat supply, the entropy increases. Very good. And it is isothermal horizontal. Now, 2 to 3. Reversible adiabatic. You know very well, reversible adiabatic. Reversible, no heat transfer is adiabatic. Reversible, no heat transfer is adiabatic. Entropy is constant. Entropy constant means it has to be a vertical line. Now observe carefully. So from 2, the point can move upwards or the point can move downwards. But it is adiabatic expansion. And in expansion, the temperature decreases. So therefore, temperature decreases means it should come down. It should come down. So therefore, it cannot move up. It cannot move up. So please observe clearly. Therefore, it should come down. I repeat, this is 2 to 3 reversible adiabatic expansion. Reversible adiabatic expansion. Reversible adiabatic is isentropic. In isentropic, the entropy remains constant. It is expansion, so temperature falls. Okay. Now, 3 to 4 isothermal rejection. Isothermal is horizontal on TS. Heat supply, entropy increases. Heat rejection, entropy decreases. On x-axis, you have entropy. Entropy decrease means left side. Isothermal heat rejection. Isothermal heat rejection. Very good. Now, 4 to 1. Adiabatic, reversible adiabatic. What is reversible? This is adiabatic, isentropic, entropy constant. Entropy constant means vertical. It is compression. Compression means what? Upwards. So therefore, this is our 4 to 1. And this is the Carnot cycle. This is the Carnot cycle on TS diagram. And already on PV diagram, we have seen. Already on PV diagram, we have seen something like this. Something like this. We have seen like this. 1, 2, 3, 4. We have seen something like this. This is the Carnot cycle. Now, which one is easy for us to represent? PV or TS? it is very easy for me to represent if we have straight lines. So therefore, Carnot cycle is a rectangle on TS diagram. Which cycle is a rectangle on TS diagram? He may be asking. It is the Carnot cycle which is a rectangle on TS diagram. And one more golden observation. On PV diagram, it is clockwise. देखो एक बार, it is clockwise. It is clockwise. And on TS diagram, yes, it is also clockwise. So the golden conclusion is, देखो एक बार, like this, like this, like this, like this. It is clockwise. This is also clockwise. So the golden conclusion is, listen carefully, a cycle which is clockwise on PV diagram will also be clockwise on TS diagram. I repeat, a cycle which is clockwise on PV diagram will be clockwise on TS diagram. Now, so from now onwards, I'll try to represent all the cycles, processes on TS diagram wherever it is required. Wherever it is required, please don't worry, please don't worry. So which cycle is represented by a rectangle on TS diagram? It is Carnot cycle. Which cycle is represented by a rectangle on TS diagram? It is Carnot cycle. It is Carnot cycle. Excellent, my dear students. So on TS diagram, please you have to be very, very, very careful. एक second इधर देखो, and you have to be very, very careful. You have to be very, very careful. Now you have to be very, very careful. देखो एक बार, please observe. Let us take a process. Let us take a process. Okay, like this, like some process. Let us assume these processes to be reversible. Let us assume these processes to be reversible. Now he may be asking you to calculate heat transfer. So for this process, let us say the process is occurring from 1 to 2 and this is occurring from A to B. Say the process is occurring from 1 to 2, it is occurring from A to B. Just project and find the area under the curve. Find the area under the curve. This area under the curve will give you heat transfer if it is a TS diagram. But please note down that only it will give for reversible process. For example, because we calculated from this ds is equal to d dash q by t, we have actually calculated from this, it is reversible. Ab dekho, there is a process something like this, and in interviews once it was asked, he gave a process that is irreversible process. Yes, he asked once in interview. So there is a process. Now already for this student for whom this question was asked, he is already in railways. He cleared IES. So this was the question asked, and the question was, they gave an irreversible process and asked him to calculate the heat transfer. And suddenly we have a habit of projecting and calculating. But please note down that it is not valid for irreversible. It is for reversible. So when irreversible is given, kindly, and just they ask, can we calculate from this diagram? That was the question. We cannot that was the question. Can we calculate heat transfer from this diagram? We cannot calculate. We have other equations to calculate, which we'll be doing a little later. So please be careful. It is only for reversible that area under the curve when projected on entropy axis on TS diagram will give me heat transfer. That is reversible heat transfer. This will not give me heat transfer. Be clear, my dear students. Okay. And similarly, if you want for this process, project इस कर्व के नीचे का एरिया, that will give me, इस कर्व के नीचे का एरिया, that will give me heat transfer. That will give me heat transfer. So area under the curve when projected on entropy axis will give me heat transfer. Please tell me, are we clear? All of you, are we clear? चलो आगे बढ़ते हैं. Now, very, very important. So be careful, my dear students. Be careful. Now, be careful. Okay. Now, combined first and second law. combined first and second law. This is very, very important. Combined first and second law of thermodynamics. Combined first and second law of thermodynamics. Chalo dekhte hai. Please stop. We know, my dear students, all of you listen. D dash Q is equal to du plus d dash W. This equation we saw, that is conservation of energy for a process, from first law we saw this. I repeat, this we saw from first law. And you can apply this for any process. You can apply this for any process. So therefore, now what we do is, please observe clearly. Now what we do is, let me replace work with PdV. Let me replace work with PdV. So what do I get? Let us say d dash Q is equal to du. I am replacing this work with PdV. And you know, my dear students, whenever I replace work with PdV, it is strictly valid for reversible process. So now I can say it is valid for a reversible process only. Okay, no problem at all. Let this be equation number 1. Let this be equation number 1, which is strictly, this is valid for any process, but this is strictly valid for a reversible process. There is no problem at all. And can I say this equation is obtained from first law? Definitely I can say it is obtained from first law. Definitely I can say it is obtained from first law. It is obtained from first law. Definitely I can say it is obtained from first law. Very good. ds is equal to d dash Q by T. And you know it is obtained from second law. It is obtained from second law. It is obtained from second law. D dash Q is equal to TDS. D dash Q, I repeat, where from we got this equation? Second law. But can anyone tell it is valid for what? Strictly it is also for reversible. Please understand carefully the origin of equations. It is also obtained for reversible. It is also for reversible. It is the first law and this is the second law. So now d dash Q is TDS. So let us take this as equation number 2. Let us try to combine first and second law. Idhar dekhna. This is the second law. This is the second law equation, and this is the first law equation. So what we try to do is, there is d dash Q. There is d dash Q. There is d dash Q. Look at. There is d dash Q. There is d dash Q. Both are equal. So मैं क्या कर रहा हूं? Just I am substituting the value of d dash Q as TDS. The value of d dash Q as TDS in this equation. फिर बता रहा हूं सुनो. We have d dash Q as TDS. So we have d dash Q. So d dash Q का value as TDS will substitute here. So I have an equation TDS. देखो एक बार. D dash Q is TDS. So TDS is equal to du plus PdV. TDS is equal to du plus PdV. TDS is equal to du plus PdV. This is our equation. This is our equation. This is our equation. Now stop. This is the combined first and second law of thermodynamics equation. Now we have to see this equation very minutely. And already we started using this equation, and these two equations in fact we have used. But these two are strictly valid for reversible. I repeat, these two are strictly valid for reversible. चलो एक बात देखते हैं हम. Listen carefully. You know, my dear students, heat transfer, work transfer, they are path functions. And all properties are point functions. So properties have nothing to do with path. Properties have nothing to do with path. Wait, तकियुद्दीन, I am coming तकियुद्दीन. अभी मैं कुछ बोला ही नहीं. तकियुद्दीन साहब थोड़ा इंतजार करो, आपको मैं पूरा जन्नत दे दूंगा, कोई फिक्र मत करना. तकी साहब, डॉक्टर तकी, थोड़ा इंतजार करो बेटा. आपका सवाल अभी देखा, मैं क्लास के मूड में था. So don't worry. Dr. Taki, listen. So you have to be ready. Your test is on Monday. Your test is first test on thermodynamics up to first law. Second law. Up to second law, not entropy. Up to second law is on Monday. I'll tell you timings. The first test is on Monday. Chalo. Now the question comes. I repeat, your first test is on Monday. All of you. Your first test is on Monday. Okay, fine. No problem at all. TdS is equal to du plus pdv. Let us say this is applicable for what? Now देखते हैं, इधर देखो. Please listen. Now, if you observe very closely, there is a path in this equation. Let us observe this equation. There is a path function. Internal energy is a property. Pressure is a property. Volume is a property. Though all these are properties, but there is a path function. There is a path function. Heat transfer is a path function. That's why it is valid for a particular path only. What is that path? Reversible. Similarly, if you take this equation, temperature is a property, entropy is a property, temperature is a property, entropy is a property, and heat transfer is a path function. So there is a path function sitting here. So that's why this particular equation is valid for a particular path, and that path is again a reversible path, and that path is again a reversible path, no problem at all. That path is again for a reversible path, no problem again. देखिए, so please देखिए. Yes. For your sake, I will schedule the test in evening only. No problem at all. Definitely. Odd timings, we'll keep it at some odd timings, like maybe 9 to 9:45 or 9 to something like it, 8:15 to 9. So I'll post it in group so that maximum views I'll take. Maximum those who say this time is suitable, so we'll consider. Don't worry. Okay, no problem at all. Now, so it was told that I don't know, but from November the session may start. I don't know. I'm not yet clear with this, but I saw in circulation some of the messages from November things are going to start. We don't know exactly. So November से शुरू हो रहे classes ऐसा सुनने में आ रहा है, but honestly I don't know, and we may not take risk so soon. चलो देखो, TdS is equal to du plus pdv. TdS is equal to du plus pdv. अब देखते हैं. Temperature is a property, entropy is a property, internal energy is a property, pressure is a property, volume is a property. Means this equation is connecting all properties. This equation is connecting all properties. This equation is connecting all properties. Now let us come back to this equation. This is not a property, it is a path function. And these are properties. See the difference. As all are not properties, that's why it is valid for a particular path only. But here all are properties. Let's see clearly, my dear students. My question to you people is, can I write ds is equal to, इधर देखना, ds is equal to, you divide with t, du by t plus p by t into dv. Can we write? एक बार देखना, ds is equal to du by t plus p by t dv. Yes, we can write. No problem at all. Now my question to you people. So from this equation, I found ds. From this equation, I found ds and I got this. Okay, देखो. Now the question is, there are 2 points, say 1 and 2. There are 2 points, say 1 and 2. There are 2 points, say 1 and 2. 1 and 2. One is reversible. The other is irreversible. One is reversible, other is irreversible, but these two processes are connected between same endpoints. Same endpoints. Now tell me, if I am using this equation, what will be the entropy change for reversible and irreversible? Already we have seen. As long as endpoints are same, as long as endpoints are same, whether it is reversible or irreversible, you will get the same answer. Means I can use this because entropy change or entropy is a property. This change will give me the same value. Suno dhyan se. This change will give me the same value whether it is reversible or irreversible. That's why this equation is valid for reversible as well as irreversible process. The reason is it is connecting all properties. There are no path functions. It is valid for all processes. What do you mean by all processes? Reversible or irreversible? Because temperature is a property, entropy is a property, internal energy is a property, pressure is a property, volume is a property. As it is connecting all properties, it is valid for any process. What do you mean by any? Reversible or irreversible? One more thing. When I was deriving this equation, I never said it is valid for ideal gas. I never said it is valid for water. I never said it is valid for steam. So is the case with this. I never said this is valid for gas, this is valid for real gas. I never use those words. So these are valid for any working fluid. फिर से बता रहा हूं सुनो. This equation is valid not only for any process, maybe reversible, maybe irreversible, but also for any working fluid. Stop. Now the question comes, is it for a closed system? Abhi मैं comment नहीं करूंगा. Give me 3 minutes. I'll talk about that a little later after 3 minutes. So right now, this equation is valid for anyone, for reversible as well as irreversible process, point number 1. And it is valid for any working fluid. What do you mean by any working fluid? What do we mean by any working fluid? What do we mean by any working fluid? Bolo, what do we mean by any working fluid? Maybe gas, maybe anything, no problem at all whatsoever, no problem at all whatsoever. Maybe steam, maybe water, maybe ideal gas, whatever it may be, it is valid. So no problem at all. Very good, my dear students. Absolutely fine. So till now, is it clear? Why this equation is, no, why TDS is equal to du plus, yes, very good. Any process, right now. अभी मैं बाद में सिस्टम के बारे में बात करूंगा अमित. वेरी गुड. सो नाउ टेल मी, TDS is equal to du plus PdV. TDS is equal to du plus PdV is valid for reversible, reversible process, irreversible process, reversible process, irreversible process, and for any working fluid. What do you mean by any working fluid? Maybe water, maybe steam, maybe ideal gas, maybe real gas, anything, no problem at all. So is it clear? Is there any problem? Is everything fine? Is everything fine, my dear students? Very good. चलो, let's proceed, my dear students. आगे बढ़ते हैं. Now, this is one equation, TDS is equal to du plus PdV. Now, let us move ahead. देखो, we know that, yeah, H is equal to U plus PV. We know that H is equal to U plus PV. And clearly I told you that H is equal to U plus PV is valid for anything. It is the generalized equation of enthalpy. Chalo. Can we write this as differentiate karo ek bar? dH is equal to du plus PdV. PV, what is that? PdV plus VdP. I repeat, dH is equal to du plus PdV plus VdP. Absolutely fine, no problem at all. Now, just now you saw, my dear students, इधर देखो, just now you saw, एक second इधर देखो, हाँ, इधर देखो, what is du plus PdV? Just now you saw du plus PdV. What is du plus PdV? D dash Q. Du plus PdV is D dash Q. So, du plus PdV, देखो एक बार, du plus PdV is D dash Q. So, this can be written as D dash Q. So, therefore, now we'll write this as dH is equal to du plus PdV is D dash Q. ये तो D dash Q है plus VdP. Now, no problem. This is from first law. Du plus PdV is D dash Q. This is from first law. We got this from first law. I repeat, my dear students. Du plus PdV is dQ. I have substituted here. We got from first law. Now, ds is equal to d dash q by t, or d dash q is equal to tds. This I got from second law. This I got from second law. This I got from second law. So what I do is, I will substitute d dash q value as tds. I'll substitute d dash q value as tds in this equation. So dH is equal to, look at dH, d dash q. What is d dash q? TDS. What is d dash q? What is d dash q? TDS plus VdP. So therefore, TDS is equal to dH minus VdP. TDS is equal to dH minus VdP. TDS is equal to dH minus VdP. This is the equation. This is again known as combined first and second law. Why is it known as combined first and second law? We have first law here, we have first law, and this is second law. This is second law. We have substituted second law in first, so we are combining first and second. I got this. This is also combined first and second law. We have one equation, that is TDS is equal to du plus PdV and TDS is equal to dH minus VdP. Look at carefully. These two are known as combined first and second law of thermodynamics. Now let us see for what processes this is used. एक second. Temperature is a property. Entropy is a property. Ariyar, it is change in entropy. Don't write D is a property. Pagal. So ds is change in entropy. Temperature is a property. Entropy is a property. Enthalpy is a property. It is difference in enthalpy. Enthalpy is a property. Volume is a property. Pressure is a property. Again, this equation is connecting various properties. Again, this equation is connecting various properties. Again, this equation is connecting various properties. I repeat. Again, this equation is connecting various properties. So therefore, whenever it is connecting properties, properties have nothing to do with path, whether it is reversible or irreversible, as long as endpoints are same. It's something like this, my dear students. TDS is equal to dH minus VdP, or ds is equal to dH by t minus V by t dP. Absolutely fine. Absolutely fine. So now tell me, if I use this equation, see, observe clearly. Let us say between these 2 points. One is reversible, one is irreversible. This equation will give me same value of entropy change, whether it is reversible or irreversible. That's why this equation is again applicable for any working fluid. Any process. What is that? Any process, reversible or irreversible, because again it is connecting various properties. And while deriving this equation, I never said it is valid for real gas, it is valid for water, it is valid for steam. I never use those words. So therefore, this equation is valid for any process, any process and any working fluid. Now let us consolidate. TdS is equal to du plus PdV. TdS is equal to dH minus VdP. Very good. Now students may be having confusion. Sir, see, that is the problem with students, not with the equation. There is no problem with the equation, but there is a problem with the way we visualize things. There is no problem with the equation. The problem is with us only, including me. Dekho. You see PdV, you see VdP. I told you that PdV is a closed system work. I'll be deriving after some time minus VdP as open system work. So you may be tempted to answer something like this. This is valid for open system. This is valid for closed system. Galat. Galat. You may be tempted to say this is valid for open system, this is valid for closed system. Absolutely wrong. Ab dekho, from this equation, I can bring this. From this equation, second equation, I can bring first. Ab dekho, ek baar dekho. TdS is equal to dH minus VdP. Okay. Now enthalpy is equal to U plus PV. dH is equal to du plus PdV plus VdP. Okay. And you know very well, du plus PdV is d dash q. Absolutely. So TdS is equal to dH is, dekho, dH is, leave it. Okay, एक second, 1 second please. TdS is equal to dH. What is dH? TdS is equal to dH. What is dH? du plus PdV plus VdP. TdS is equal to dH. What is dH? du plus PdV plus VdP. अरे यार dH का वैल्यू सब्स्टिट्यूट किया हूं. TdS is equal to dH. What is dH? du plus PdV plus VdP minus VdP. So TdS is equal to du plus PdV. अरे यार अगर ये केवल ओपन सिस्टम के लिए अप्लीकेबल है तो बट आई गॉट दिस. This enthalpy is the generalized equation which is applicable for open as well as closed system. This is the generalized equation. If this is applicable for open system, this should also be applicable for open system. Na? Similarly, from this equation, I can get this equation. मतलब both यहां से ये आ सकता, ये निकाल सकता. From this I can get this. From this I can get this. So both are valid for any system, whether it is open or closed system. देखो, we can use these equations for open as well as closed system, and in PK Nag book at some point it is given as this is valid for closed, this is valid for open, but he has corrected later on. By mistake it was given, I don't know, so he has corrected. But please note down that ये दो equations there is no limitation. जहां चाहिए वहां यूज कर सकते. फॉर द फर्स्ट टाइम आई एम गिविंग यू इक्वेशंस वेयर देर इज नो रेस्ट्रिक्शन, नो लिमिटेशन. सो TdS is equal to du plus PdV, TdS is equal to dH minus VdP. You have every liberty to use. देखो, फ्रॉम दिस, मान लो ये ओपन के लिए है, बट आई गॉट दिस, but this were closed. You may be thinking galat. So both are used for open, both are used for closed, both are used for reversible, both are used for irreversible, both are used for any working fluid. So this is the beauty of the equation. So now we have two strong weapons without any limitations. Matlab, these two weapons are going to fight anywhere. So if you throw him into the open system, he will go and fight. If you throw him into the closed system, he'll go and fight. If you throw him in ideal gas, he'll fight. So if you throw him in reversible, yes, he is ready. So these two are, I consider, as the twin equations of entropy, and which are very powerful equations, and I'll be solving about 70 to 80% of questions from these two equations only. And we have to respect these two equations a lot. They are not only valid for any processes, any system, and also for any working fluid. Please tell me, are we clear? All of you, are we clear? All of you, are we clear? So keep it in mind, TDS is equal to du plus PdV, TDS is equal to dH minus PdV. Keep it in mind. They are very, very powerful equations. They are very, very powerful equations. Very powerful. Very powerful equations. Clear? Clear, all of you? Very good, my dear students. Excellent, 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 excellent. Very good, very good. Yo. Jakan Baba, crystal clear. Okay. Now, representation of constant volume and constant pressure processes on TS diagram. Representation of constant volume and constant pressure processes on TS diagram. It is very easy to represent constant pressure and constant volume on PV diagram, because volume constant means vertical, pressure constant means horizontal. On PV there is no problem, but now I wish to represent it on TS diagram. Okay, please stop. Please stop. We know, my dear students, TDS is equal to du plus PdV. TDS is equal to du plus PdV, and this is the most generalized equation I can use for any process, any system, any working fluid. Okay, now look at, my dear students, there are terms known as specific quantities. Extensive properties, when they are divided with mass, you get what? Specific properties. There is nothing like temperature by mass is small t. There is nothing like pressure by mass is small p. Galat. Entropy is extensive. Internal energy is extensive. Volume is extensive. Entropy is extensive. Internal energy is extensive. Volume is extensive. No problem at all. Very good. Now, yes. No problem at all. No problem at all. No problem at all. Absolutely no problem at all. Dekho. Now I'll divide with mass. Dekho ek bar. So what do I get? So no, it is T. Entropy by mass, I'll write it as specific entropy. Internal energy by mass, small u, specific internal energy. Pressure is P. Volume by mass is specific volume. Means I can write the equation like this. I can write the equation like this or like this. Consistent units. Very good. Now, please observe clearly. You can take either this or this. There is no problem at all. You can take either this or this, no problem at all. Chalo ye le lenge. You take either this or this, no problem. Let's take TdS is equal to du plus TdV. Let us take constant volume process. And you know, when volume is constant, the change in volume is zero. When volume is constant, the change in volume is zero. So I can write this as idhar dekhna, TdS is equal to idhar dekho du dv is zero. Change in volume is zero. Change in volume is zero. Change in volume is zero. P into zero is zero. So therefore plus zero. Okay. Now I will write TdS is equal to du. Please stop. मैं आपको कुछ अलग बता रहा हूं, सुनो. Which process have you taken? इधर देखो, कौन सा प्रोसेस लिए आप? Constant volume. And you know, my dear students, when I go to my thermodynamic relations, du is equal, actually look at, if it is capital U, it will be mCv dt, and du by m is equal to Cv dt. d of u by m small u is Cv dt. Dekho, please observe. If it is capital U, it will be mCv, du is mCv dt, du by m small u Cv dt. Ab dekho, I have told you in my earlier class, in fact I am going to derive this equation. Please look at carefully. Du can be, small u, dekho ek baar, small u can be written as Cv dt for ideal gas for any process. But for real gases also this is valid only when the process is constant volume. And I am going to derive this equation. du is equal to Cv dt is valid for ideal gas for any process. du is equal to Cv dt is valid for real gas only for constant volume. But it is constant volume. Therefore, this can be applied for real gas as well as ideal gas. Why? Because if it is ideal gas, there is no problem. If it is ideal gas, there is no restriction on process. Arey yaar, all these equations I am going to derive in thermodynamic relations last chapter. You don't have to worry about that. So now what I am saying is, du is Cv dt. If it is ideal gas, there is no restriction. You can apply freely. But if it is a real gas, this is valid only for, अरे यार, already अगर ideal gas है, so there is no limitation of this equation. There is no limitation of this equation. You can use whatever the process the system is undergoing. If it is ideal gas, du is equal to Cv dt, you have liberty. But this equation can also be used for real gas only when the process is constant volume. Already it is constant volume. So this is applicable both for ideal gas and real gas. Both for ideal and real gas. Because we are taking constant volume. Means whatever the equation I am going to derive now, it is valid both for real as well as ideal gas. ये बहुत carefully देखना है. So why you took as constant volume? You took the process as constant volume. For du is Cv dt is valid for real gases only under constant volume conditions. But already it is constant volume, so it is valid for real gases. But if it is ideal gas, it is universally accepted for all processes. So now whatever I am going to derive, it is valid for all. Idhar dekhna. So we have TdS is equal to du. But what is du? Cv dt. What is du? It is Cv dt. What is du? What is du? Cv dt. So therefore I write this as, of course ये small s है, dt by ds is equal to, इधर देखना, dt by ds is t by Cv. dt by ds is t by Cv. Now observe clearly. dt by ds is dt by ds is T by Cv. dt by ds is T by Cv. Can anyone tell on Ts diagram what is dt by ds? इधर देखो, dy by dx, dy by dx, dy by dx, it is slope. This is the slope. किसका स्लोप है ये? कांस्टेंट वॉल्यूम. किसका स्लोप है? कांस्टेंट वॉल्यूम. सो स्लोप ऑफ कांस्टेंट वॉल्यूम, and that is equal to T by Cv. So on Ts diagram, the slope of constant volume is T by Cv. Everyone knows Cv is always positive. Already have explained. Cv only polytropic specific heat is negative. Other specific heats are positive. And capital T, Kelvin temperature is always positive. So positive by positive is positive. Matlab constant volume slope on Ts diagram bear positive slopes. If you are plotting, you are getting something like this. Yes, it is a positive slope. What do you mean by positive slope? When can this be positive? When change in temperature is positive, change in entropy is positive. When both are positive, then only it will be positive. When this is negative, this should be negative. So when both are negative, negative by negative is again positive. Is that? For example, you take point 1, you take point 2. See what is happening. What is happening? T2, T1. So temperature is increasing from 1 to 2 and entropy is increasing from 1 to 2. So it is a positive slope, positive slope, positive slope. So please note down that this equation is valid for any gas. What do you mean by any gas? Ideal or real, because we have derived for constant volume. And this is very, very important, very, very important. Now finally I'll put like this. The slope of constant volume process on Ts diagram is equal to T by Cv, and this is valid for real and ideal gases. This is valid for real and ideal gases, real and ideal gas. And on PV diagram, isothermal and adiabatic slopes are negative. Already we have seen minus P by V. Yes. See, whatever I had discussed, all of you have you followed? Whatever I had discussed, all of you have you followed? Please tell me, all of you have you followed? जो भी डिस्कस किए, इज इट क्लियर? कम ऑन, आई एम वेटिंग. आई एम वेटिंग. Clear, clear, clear? All of you. So if you permit me, I'll proceed. Clear? आगे बढ़े? बोलो बोलो. Excellent, excellent. Excellent, my dear students. Excellent. Awesome, awesome. Chalo. Now, let us go for constant. We have seen how do we represent constant volume on Ts. Let's see how we represent constant pressure on Ts. Idhar dekhna. Look at representation of constant pressure on Ts. Okay. We know that TdS is equal to dH minus VdP. TdS is equal to dH minus VdP. देखो, both sides I'll divide with mass. Both sides I divide with mass. Both sides I divide with mass. So this can be written as entropy by mass, I'll write it as small s. Enthalpy by mass, I'll write it as small h. Volume by mass, specific volume, dP. Okay, कोई बात नहीं. Either I can use this or this, both would give me same meaning, because if you want total, I'll multiply with mass. If you want specific, I use this equation. No problem at all. Ek baar. Let us take constant pressure or isobaric process. When the pressure is constant, the change in pressure is obviously zero. So let us take up this equation. TdS is equal to dH minus VdP. What is dP? Zero. dP zero hai, to ye zero hoga, dH. Okay. Now, my dear students, what is the process? What is the process? Constant pressure. What is the process? Constant pressure. The process is constant pressure. The process is constant pressure. And for constant pressure, dH is equal to Cp dt, or d capital H is equal to mCp dt. So if I divide with mass, it will be d small h is Cp dt. No problem at all. No problem at all. Okay. So no. Can you tell me under what conditions it is valid? I told you very clearly. If it is an ideal gas, there is no limitation. If it is an ideal gas, there is no limitation. You can use it for any process. For ideal gas, there is no limitation. But this equation can be used for real gases only under constant pressure. And this will be derived in my last chapter. Don't worry. For real gases, this equation is applicable only when the pressure is constant. But already the pressure is constant. When already the pressure is constant, now this is valid for ideal as well as real. I repeat, my dear students, this is valid for ideal or real. This is valid for ideal or real. Why? Because already we took the pressure as constant. Already we took the pressure as constant. When the pressure is constant, it is applicable for real. But for ideal, there is no limitation. So whatever I am going to do now, it is valid both for ideal as well as real gases, because under constant pressure, this is absolutely valid. No issues at all. So therefore, now let's use this equation. Ek second. Let us use this equation. Dekho. TdS is equal to dH, but everyone knows dH is equal to, everyone knows dH is equal to Cp dt. So therefore, TdS is equal to dH, but dH is Cp dt. dH is Cp dt. TdS is equal to dH. So dH is what? Cp dt. So dt by ds is equal to, dt by ds is T by Cp. Absolutely fine. Can you tell me what is dt by ds? If you take any plot on Ts diagram, what is dy by dx? dy by dx slope. So dt by ds is slope. किसका slope है ये? ये किसका slope है? Constant pressure का. So therefore, constant pressure slope on Ts diagram is T by Cp, and constant volume slope is T by Cv. Everyone knows Cp is positive and T is absolute temperature is always positive. It cannot be negative. So therefore, again, the slope of constant pressure lines on Ts diagram is positive. So if you plot this, you have something like this. You have something like this, because when T is increasing, the entropy is also increasing. It is positive slope. It is positive slope. Huh? The slope of constant volume is derived from TdS to d. It can be valid for other working fluid. See, again you are committing one mistake, my dear Taqiyuddin Saab. No doubt that I have used this equation. No, Taqiyuddin Saab, no doubt I have used this equation. It is valid for anything. But apart from this, I have used this condition now. I have used this condition now. How can you use this condition for water? How can you use this condition for steam? It is valid only for gases. So I have put that condition. Yahan tak there is no problem. Till now there is no problem. But I have used some conditions of ideal gas. That's why from here onwards it is valid for real or ideal gas. From here onwards. Because I have put a condition which is valid only for certain section of working fluids. So this equation is used only for certain fluids. So therefore, I cannot use this. Please observe clearly. This is valid for anything, as you said. I have no problem. But I am putting, yahan tak koi problem nahi. But I am putting this condition in this. But this is valid only under limited cases. That's why from here onwards it is for limited cases. So ये condition आप सबके लिए use नहीं कर सकते. And don't think that ये तो सबके लिए है. See, initially it is for all. But now from there, I took dH is equal to Cp dt. It is for all. TdS is equal to dH minus VdP. It is for all. But यहाँ आने के बाद dH is equal to Cp dt. So from now onwards, only those satisfy this will be for those fluids I should use. अरे तकियुद्दीन साहब समझ में आया? Very good. Excellent. Understood now? Chalo. Now, let us superimpose both. Please note down that it is on TS diagram. It is on TS. Slope of constant pressure T by Cp. Okay. Now let us try to see. Dekho. Now I am asking you a question. Which one has more slope? Now I am asking a question. Which one has more slope? Ek second dekhna. Everyone knows at a given point I am checking the slope. When I say at a given point, my temperature is same. At a given point, temperature is same. But one has Cp, other has Cv. Everyone knows Cp is greater than Cv. Cp is greater than Cv. When Cp, but it is in denominator. When Cp is more, when it is in denominator. When Cp is more, it is in denominator. When this is more, this value will be less. So which slope will be less? Constant pressure. Cv is less. CV कम है. 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 So जब CV कम है तो ये कम है तो स्लोप क्या होगा? ज्यादा होगा. तो किसका स्लोप ज्यादा होगा? Anyone? किसका स्लोप ज्यादा होगा? Constant volume. So if you are plotting both, for example, one I got like this, the other I got like this. Dekho, please observe. So at a given point, more slope, all of you observe. Why are you at a intersection point draw horizontal line? Why horizontal line? Slope is dy by dx. It is represented with respect to x-axis. That's why draw a horizontal line, x-axis. But why are you drawing positive x? Because these slopes are positive. There in isothermal adiabatic negative to hum piche liye the, but now positive. Let us take this angle theta 1. Let us take this angle theta 2. Which angle is more? Theta 2 means more slope means constant volume. Less slope means constant pressure. More slope. So therefore on TS diagram the constant volume and constant pressure lines are something like this, something like this. ये देखो, ज़्यादा slope is constant volume, कम slope is constant pressure, more slope is constant volume, less slope is constant pressure. अरे बाबा, are we clear? चलो, ये सब it will be useful in Otto cycle, diesel cycle. These things will be useful in Otto cycle and diesel cycle, where we'll be discussing everything in detail. So just remember that these same question can be asked in assertion and reasoning also. How it is asked in assertion and reasoning? Either dekho, assertion, same question can be asked in assertion and reasoning. Assertion: the slope of constant pressure lines is greater than the slope of constant volume line. देखो कैसा confuse करेगा. The slope of constant pressure lines is greater than slope of constant volume lines. Assertion, reason: Cp is greater than Cv. Oh my God. You may be tempted to answer Cp is greater than Cv, therefore slope of constant pressure is greater than slope of constant volume. Hence both are correct, and supporting answer A, galat. It is wrong. It is the slope of constant volume greater than the slope of constant pressure. Why we are taking you represent slope with respect to what axis? You represent the slope with respect to what axis? dy by dx. dy by dx. 1 second please. Good morning sir. నేను క్లాస్ లో ఉన్నాను సార్. చెప్పండి. ఓకే, అవునా, నేను క్లాస్ అయ్యాక మాట్లాడానా సార్ ప్లీజ్? షూర్. ఓకే. Listen. What are these slopes? Are these slopes positive or negative? अरे अभी तो बताया both are positive बोल के. तो at the intersection point, draw x-axis. Why are you drawing x-axis? Because slopes are represented with respect to x-axis. dy by dx. It is not dx by dy. It is dy by dx means it is with respect to x-axis. So why are you drawing positive? Because my slopes are positive. So इसलिए intersection points are positive x-axis. So this is the angle. Hariyar, have you followed? Have you followed, my dear students? Have you followed, all of you? Very good. Let's proceed. Yeah, why should I erase? Yes. Please look at all of you. Now, so whatever I am going to discuss now, it is again very important. Now, let us try to find out entropy change for solids, for liquids, for gases. Generally for gases we deal with ideal gases. Mostly we have air, nitrogen, argon. Mostly they are ideal gases. So let me take up the case entropy change of an ideal gas. 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 Okay, fine. Let's see how do we calculate. You know, my dear students, please all of, now we are trying to find out the entropy change for ideal gas. Okay, Takyuddin Saab, idhar dekho. Let us take the equation TdS is equal to du plus PdV. Is it valid only for ideal gas? No, it is valid for anything. But if I put ideal gas conditions in this equation, then it will be valid only for ideal gas. I repeat, my dear students. This equation is valid for any gas, any working fluid, no matter what the fluid is. But if abhi tak we have not put any conditions, so as such it is valid for anything. But if I start substituting conditions of ideal gas in this, so they are valid for only ideal gas. Chalo, now, what do you want? See the heading, entropy change. Where is this entropy change? Here. So I write this as ds is equal to du by t plus p by t into dv. I write this as ds is equal to du by t plus p by t dv. Please stop. For an ideal, now in this equation no conditions are put. Up to this it is valid for anything. But now for an ideal gas, du is mcv dt. Look at my dear students. I never said it is a constant volume process. In previous case, we found slopes for constant volume and constant pressure. That's why I use constant volume, constant pressure. But simply I'm saying an ideal gas is undergoing a process. That process can be anything. An ideal gas is undergoing a process. That process can be anything. An ideal gas is undergoing a process, and that process is anything. Is anything. An ideal gas is undergoing a process, and that process is anything. What do you mean by anything? Maybe constant volume, maybe constant pressure, maybe isothermal, maybe adiabatic, maybe polytropic. No problem at all. No problem at all. So therefore, for an ideal gas, I can write du is mcv dt and PV is equal to mRT. But these two, please note down that I never said, I simply said ideal gas. If it is an ideal gas, this is valid for ideal gas, this is valid for any process. What do we mean by any process? This gas may undergo constant volume, this gas may undergo constant pressure, this gas may undergo adiabatic, this gas may undergo polytropic, or any process. So I am trying to derive a generalized equation for change of entropy when the working fluid is ideal gas. I am not putting any limitation on a particular process, but the only limitation that I am putting is ideal gas. So now when the ideal gas, when our working fluid, which is an ideal gas, undergoes any process, I use these equations. There is no restriction on the type of process. Okay. So ds is equal to du. What is du? mCv dt. ds is equal to du. What is du? mCv dt by t. ds is equal to du by t. Du is mCv dt by t plus p by t. Now tell me what is p by t. Anyone? What is p by t? It is mr by v. I repeat. So p by t is mr by v. So p by t is mr by v. Okay, mr by v into dv. Now I have just up dekho. From now onwards, it is valid only for ideal gas because I have used PV is equal to mRT in this equation, which is strictly valid for ideal gas, and I have used du is equal to mCv dt, which is valid for ideal gas. So from now onwards, the equation is valid only for ideal gas. But till now, no limitation was put. Till now, it is valid for anything. But from when I put these conditions, it is valid only for ideal gas. Let us integrate this. The entropy is changing, say from S1 to S2. Here it is dt. So temperature is changing from T1 to T2. Here it is dV, volume is changing from 1 to 2. We are trying to find out the entropy change undergone by an ideal gas, any process. That ideal gas may undergo constant volume, maybe constant pressure, any process. But we are trying to find out the entropy change for ideal gas. Okay. What is integral ds? What is integral ds? S का मतलब upper limit minus lower limit. S2 minus S1. Listen carefully. Mass is constant. And one more thing. Generally, the specific heat is treated to be constant, but sometimes he will give you variation of specific heat with temperature, something like A plus KT. When he gives this as a function of temperature, do not take it out. But most of the times it is treated to be constant. But if it is a function of temperature, put here and integrate. But यहाँ पे let us assume specific heat to be constant. When specific heat is constant, take it out. So mass is constant, CV is out. What is dt by t? What is dt by t? Log t, log t, log t2 minus log t. I repeat, integral dt by t is log t. Log t2 minus log, upper limit is t2, lower limit is t1. Log t2 minus log t1 is log a minus log b is log a by b. And all these in entropy, please listen. We started with Q by T. entropy, and this we started with Kelvin. So always remember, in entropy, actually Q1 by T1 is equal to Q2 by T2. We started from there, and their temperatures are in Kelvin. So in entropy, temperatures must be taken strictly in Kelvin. In entropy, temperatures must be taken strictly in Kelvin, even if he is not asking. Please, any working fluid, you should take it in Kelvin. The reason is, we started with Q by T. In that particular T is in Kelvin. So you should be very, very careful. Plus, R is constant, take it out. R is constant. What is dV by V? Log V. Log V2 minus log V1. So log of V2 by V1. Very good, my dear students. Now, if I divide this with mass, what do I get? Both sides divide with mass. Capital S becomes small s. When I'm dividing with mass, it will be S1. Divided with mass, CV ln T2 by T1. Divide with mass, R ln V2 by V1. This is my equation for the change in entropy. But please note down that it is valid only for ideal gas. Maybe any process. Maybe any process. What do you mean by any process? The ideal gas may undergo constant volume, may undergo constant pressure, may undergo isothermal, it may undergo adiabatic, it may undergo polytropic. You can use this equation. The only condition that is required for applying this equation is the working fluid must be an ideal gas. Apart from that, there is no other restriction. A student may ask me a question, sir, why have you used this equation? We have one more equation now. Why you have not used? Yes, my dear students, I can use that also. I'll get one more. Means I can use this or that. I'll get this same result. So let us try to see if I use that, if possible. Listen. I found maximum questions on entropy on ideal gases. And I advise you to remember, if possible, the equation. Because in examination it may take time to derive and you may be wasting time. Therefore, it's advisable to remember this equation, and all these temperatures are strictly in Kelvin. Suno. This equation is used generally when volumes and temperatures are given. When volumes and temperatures are given, V2 by V1, T2 by T1. When volume temperatures are given, okay, no problem at all. Now, let us take one more equation, that is TdS is equal to dH minus VdP. Let us take one more equation, TdS is equal to dH minus VdP. Okay, now observe here. I want the entropy change, that is dH by T minus V by T into dP. देखो, ds is equal to dH by T minus, I want the entropy change. Till now I have not used any condition, so it is valid for anything. Now, for an ideal gas, dH is equal to mCp dt and PV is equal to mRT. V by T, what will be V by T? What will be V by T? It is mR by P. What will be V by T? V by T, mR by P. So ds is equal to, इधर देखो, dH by T. What is dH? What is dH? What is dH? mCp dt. dH is mCp dt. देखो, dH is mCp dt by T minus V by T. What is V by T? mR by P. What is V by T? V by T, mR by P into dP. let us integrate this equation from S1 to S2 and dt T1 to T2 and dp P1 to P2. So therefore integral ds is S का मतलब S2 minus S1. Integral ds is S का मतलब S2 minus S1. Mass is constant. Let us assume specific heat to be constant Cp. What is dt by T? Log T. dt by T is log T. Log T2 minus log T1 is ln T2 by T1 minus mr. M is constant, R is constant. What is dp by P? Log P. Log P2 minus log P1 is log P2 by P1. No problem at all. Divide both sides with mass. So divide with mass. Small s2 minus small s1 is divided with mass ln. Again temperatures are strictly in Kelvin. Minus R ln P2 by P1. Very good. Again this equation is valid only for ideal gas. Can you tell me why it is valid only for ideal gas? Because we have used all ideal gas conditions like P is equal to MRT we have utilized in this equation. So it is strictly valid for ideal gas. Means I told you very clearly Biswadas this equation is valid for reversible, irreversible. When I use PV is equal to MRT, did I ever say it is reversible, irreversible? No. So यहाँ पे there are no conditions of reversible or irreversible. The only condition is ideal gas. You can use it for reversible, irreversible, anything. But the only thing is it should be ideal gas. It should be ideal gas. Now and when are you using this equation? This equation must be used generally when pressure, temperatures are given. It should be used when pressure, temperatures are given. Is it okay? Chalo. Now, the first equation that I gave is when pressure volumes are given. The first equation, pressure volumes are given. First equation, pressure volumes are given. Second, याद रख लेना, TDS, what is that? CV ln T2 by T1 plus R ln, एक second, let me check. CV ln T2 by T1 plus R ln V2 by V1 is the first equation. And the second equation is CP ln T2 by T1 minus R ln P2 by T1 is the second equation, Now, I can also give you in terms of the other equation. Yeah, I can also give you in terms of other. What is that? Idhar dekho. What is the first equation? Let us take small s2. Dekho. S2 minus S1 is CV ln T2 by T1 plus R ln V2 by V1. I gave you this equation. Just now I gave this equation. Okay, stop. Let me try to write it in different fashion. Cp minus Cv can be written as R because it is valid for ideal gas. So therefore, S2 minus S1 is equal to Cv ln T2 by T1 plus R. What is R? Cp minus Cv ln V2 by V1. Absolutely. So therefore, S2 minus S1 is equal to Cv ln T2 by T1 plus Cp ln V2 by V1. Okay, Cp ln minus Cv ln V2 by V1. Absolutely fine. So therefore, S2 minus S1 is equal to Cv. Let us take Cv common. ln T2 by T1. Okay, let us take Cv common. ln T2 by T1 minus ln V2 by V1. Okay, Cv को common लीजिए तो ln T2 by T1 minus ln plus you take Cv common तो ये बचा है Cp ln V2 by V1. Absolutely. So this can be written as S2 minus S1 is equal to Cv. देखो log A minus log B is log A by B. So therefore it will be ln, देखो log A minus log B is log A by B. So therefore it will be T2 by T1 by V2 by V1. By V2 by V1. So it will go to the top. It will be V1 by V2 plus Cp ln V2 by V1. Absolutely fine. No problem at all. And you know, my dear students, PV is equal to MRT, or PV by T is equal to MR. Mass is constant, R is constant, so this is constant. So I can write this as, okay, PV by T is constant, so we can write it as P1 V1 by T1 is equal to P2 V2 by T2. So what do you want? T2 V1 by T1 V2. T2 V1 by T1 V2. T2 V1 by T1 V2 is equal to P2 by P1. So therefore, now, therefore, S2 minus S1 is equal to CV ln. What is T2 V1 by T1 V2? T2 V1 by T1 V2, P2 by P1. T2 V1 by T1 V2, T2 V1 by T1 V2, P2 by P1 plus Cp ln V2 by V1. And this is the equation. So far, I give you 3 equations and all are strictly valid for ideal gas, any process, reversible, irreversible, anything, ideal gas. So now let us put all the 3 at one place. Let me put all the 3 at one place. 1 second dekhna. Let me put all the 3 at one place. S2 minus S1 is equal to CV ln T2 by T1 plus R ln V2 by V1. S2 minus S1 is equal to Cp ln T2 by T1 minus R ln P2 by P1. And S2 minus S1 is equal to CV ln P2 by P1 plus Cp ln V2 by V1. This is the first, this is the second, and this is the third. And all these are valid only when the working fluid is an ideal gas. No other condition, no other condition. So the first must be used when volume temperatures are given. Second must be used when pressure temperatures are given. Third must be used when pressure volumes are given. And remembering this equation is very easy. When you have CV, when volume is there, pressures will come. When pressure is there, volumes will come. CV, V aa gaya to P, P aa gaya to V. Remembering is very easy. So we have found the entropy change for gases, that is ideal gas. Right. Let's try to find out entropy change for solids oblique liquids. Let's try to find out the entropy change for solids oblique liquids. Okay. We know that I said very clearly the powerful equations are this. TdS is equal to du plus PdV, or TdS is equal to dH minus VdP. These are very powerful equations. These are very, very powerful equations. Okay. Entropy change for solids oblique liquids. Let's try to find the entropy change. Already we have found for gases, which we took, I gave in 3 forms for ideal gases. Okay, now let's try to find out for solids and liquids. You know, my dear students, if you take solids as well as the liquids, they are incompressible. What do we mean by incompressible? अरे यार, you take a solid, compress it. You take a solid and compress it. इधर देखो इधर. There is no change in the volume. Even if there is a change, insignificant. Take water in a container and try to add weights, increase the pressure, compress. You don't find. So the change in volume for solids and liquids is very negligible, and hence we call them as incompressible. Incompressible means volume is constant. Incompressible means volume is constant. Incompressible means volume is constant. That is, the change in volume is equal to 0. Incompressible means the volume is constant. That is, incompressible means the volume is constant. That is, change in volume is 0. Change in volume is 0. Okay, no problem at all. I cannot apply this incompressible theory for gases because in case of gases, when a process is carried out, there is a significant change in volume. So change in volume cannot be equated to 0 for gases. So whatever I am giving now, it is for liquids and solids. So they are incompressible, the volume is constant. So change in volume is 0. So therefore, TdS is equal to du. And what is the change in volume? What is the change in volume? What is the change in volume? It is 0. It is 0. So therefore, now please note down that this is the equation. Please note down that du is equal to, for any working fluid, we can write it as mc dt. See, note down that I have not written it as CV. I have not written as CV. So if I write CV, it is for ideal gas, but it is not ideal gas. It is solid or liquid. For any working fluid, the internal energy change can be written as mc dt. If it is an ideal gas, then we write CV, but it is not an ideal gas. For any working fluid, the internal energy change is mc dt. And you know, solids and liquids, they have only one specific heat, that is say C. Therefore, I wrote this. Okay, now TdS is equal to, in entropy, all temperatures are in Kelvin. Long back I have told you, keep it in mind. Keep it in mind. Okay, TdS is du. What is du? mc dt. du is mc dt. So ds is equal to mc dt. ds is mc dt by t. Okay, no problem at all. Let us proceed, my dear students. Let us proceed. So therefore, ds is equal to mc dt. Okay, and please note down that these temperatures are in Kelvin. Let us integrate. Let us integrate. So entropy hai, so let it be initial entropy. Let it be final entropy, or S1, S2. 1 is initial, 2 is final, or SI, SF. Similarly, dt hai initial temperature, final temperature. It is initial temperature, final temperature, T is in Kelvin. Now, what is integral ds S? What is integral ds S? S ka matlab final minus initial. So it is SF minus SI. And that is equal to, if the specific heat is not varying with temperature, take it out. So therefore it is MC. MC is taken out. MC is taken out. If the specific heat is a function of temperature, you cannot take it out. What is dt by T? Log T. Log TF minus log TI. So it will be log TF by TI. It is log TF by TI. And this is the equation of entropy change for solids oblique liquids. So now we are ready with 3 types of matter. Now we are ready with 3 types of matters. What are those? Gases already I give you, solids, liquids bhi aapke paas hai. So now we are ready to calculate the entropy change for any working fluid, maybe solid, maybe liquid, maybe gas. So no problem at all. So therefore these temperatures are strictly in Kelvin. And to confuse you, he may be giving in centigrade, convert in Kelvin. M is the mass of solid or liquid, C is the specific heat, and ln Tf by Ti. And sometimes he will give you specific heat as a function of temperature. And some students blindly, they remember this. This equation is derived by taking specific heat constant which is not varying with temperature. But if C is a function of temperature, then you cannot take it out. Put that as a function of temperature and integrate this equation. Very good, my dear students. Very, very good. No problem at all. Absolutely fine. Now we have found the entropy change for solids, liquids and gases. Now let's go to entropy change of a reservoir. Entropy change of a reservoir. Entropy change of a reservoir. We have two types of reservoirs, source and sink. We have two types of reservoirs, source and sink. Let us try to find out the entropy change for source, entropy change for sink. No problem. Look at it. Let this be source. Let this be sink. Let the source be at a temperature T1. Let the sink be at a temperature T2. Source is a supplier of heat. Sink is the absorber of heat. And you know clearly, when it is supplying heat, its temperature is not changing. When it is absorbing heat, its temperature is not changing. Okay. Now let us try to find out the entropy change for source. Okay. Let's try to find out for source. Let's try to find out for source. And these temperatures are strictly in Kelvin. I know I am shouting. In entropy, keep temperatures in Kelvin. No, Ramana Kumar, we can write. I'll tell you under what conditions we have to write. When I take pure substances, definitely I'll tell you. Definitely I'll tell you. Don't worry. Okay. Now let's see, how do I write the entropy change for a reservoir? I'll tell you, Mr. Ramana Kumar, don't worry. I'll tell you clearly, when we go to pure substances, under what conditions we write, I'll be telling you very, very clearly. You don't have to worry about that. And you have asked a very right question. You asked a very, very right question. So no problem. Chaliye. And don't worry, on KAME I'll be teaching metal forming also. Don't worry, metal forming. In production I'll be taking that part that is metal forming. You don't have to worry. So, okay, right. Now all of you, are you, please let me discuss with you for about 1 minute. Are you happy with the subject? Are you happy with the subject? बोलो, फर्स्ट विल इंटरेक्ट. एक दिन हम जूम कॉल पे सब लोगों का फेस देखते हुए इंटरेक्ट करेंगे. Are you really happy with the subject or not? If not, we'll stop. No issues, because nothing should be at your cost. Clearly बोलो आप, clearly. Very, very happy. Okay. Extremely happy. Okay. Okay. Chalo. Now, let's not waste time. Please observe, my dear students. I told you very clearly in my earlier classes, source and sink. Source, it is supplying, still its temperature is constant. Sink, it is absorbing, still its temperature is constant. Source, it is supplying, still its temperature is constant. Sink, it is absorbing, still its temperature is constant. Thank you, Takyuddin Saab. Thank you. Okay, source, though it is supplying, its temperature is constant. What does it mean? इसका मतलब है, इधर देखो, ये सोर्स है, इट इज सप्लाई, इसका टेम्परेचर T1 है, इट इज सप्लाइंग Q1. It has got infinite amount of thermal energy, even though it is supplying, its temperature is not changing. इसका मतलब क्या है? Every time the temperature is constant. When it is constant, every time it is in equilibrium. Every time it is in equilibrium. कोई चेंज नहीं है. Every time it is in equilibrium. देखो एक बार अरे यार, it is losing heat. But in reservoir, what is happening to the temperature? It is losing heat. What is happening to the temperature? What is happening to the temperature? Don't say same energy. No. It is losing heat. Still the temperature is constant. It is gaining heat. Still the temperature is constant. Means when temperature is same, I say it is in equilibrium. It is in every time it is in equilibrium. रिवर्सिबल में तो हमेशा इक्विलिब्रियम में ही होता है. ऑल पॉइंट्स आई कैन ट्रीट इट समथिंग लाइक रिवर्सिबल बिकॉज कोई टेम्परेचर में फर्क नहीं है. कोई टेम्परेचर में फर्क नहीं है. आई एम टॉकिंग नॉट फॉर ऑल दिस, आई एम टॉकिंग ओनली फॉर सोर्स. सिर्फ सोर्स की बात कर रहे हैं हम. आई एम नॉट टॉकिंग व्हेन द हीट इज सप्लाइड सराउंडिंग्स के बारे में. आई एम नॉट टॉकिंग. डेफिनेटली व्हेन हीट इज सप्लाइड बाय सराउंडिंग्स का डिसऑर्डरनेस चेंज होगा, ये वो बात नहीं कर रहा हूं. आई एम टॉकिंग only for source. So the entropy change of source is every time it is in equilibrium. Every time it is in equilibrium. When every time it is in equilibrium, no change in temperature, I can use reversible equations. For reservoir, that is source. What is ds? dq by t. But what is the heat? Q1. dq by t. ds is dq. अरे यार, ds is equal to d dash q by t. But it is for reversible. One may be asking a question, sir, it is for reversible. Why are you using? अरे सुनो, my reservoir, though it is losing it, its temperature is constant. Every time it is in equilibrium. इसमें कोई फर्क नहीं है. No changes. So therefore, for source, I can use this equation. Source के लिए, not for other things. Because every time the temperature is same. And one more thing, source is losing. We are writing for source. Source is losing. तो ये क्या होगा? माइनस क्यू होगा. Source is losing. So ये क्या होगा? माइनस Q1 होगा. And the temperature is what? T1. It should be in Kelvin. This is the entropy change for source. Now let us try to write the entropy change for sink. सुनो ध्यान से. And again the sink is absorbing, but its temperature is constant. So it is in equilibrium. So I write this equation. Every time it is in equilibrium, so कोई temperature में फर्क नहीं है. So I write the equilibrium equation. Okay. So but my sink is gaining. Sink, I am writing for sink. Sink is gaining. So it is plus Q by T. It is T2. So please note down that for source it is minus Q1 by T1 or minus Q by, why it is minus for source? Because source is losing, minus Q by T, and sink is Q2 by T2. Are Baba, are we clear? So we have calculated the entropy change for source, sink, all those things. Excellent, my dear students. Now let us proceed clearly. Aram se. These are all very, very important things. Chalo. Now, please stop. I gave you one equation, ds is equal to d dash q by t plus del s generation. I gave this equation. Do you remember this equation? I gave this equation. Yes, sir. I gave this equation. Yaad rakhna. We have an equation ds greater than d dash q by t. So I equated. So as this is more, this is less. So I added something. And we call this as entropy generation. And yesterday we saw entropy generation is not a property. It is a path function. Okay. It is an inexact definition. Ek second. Please suniye carefully. You know, my dear students, when you are adding something, subtracting something, equating something, all must have same unit. Otherwise, you cannot do it. All must have same unit. Otherwise, you cannot do it. Otherwise, you cannot do it. So my question to you people is, if this is entropy equal, so this quantity must also have the unit of entropy. This must also have the unit of entropy. फिर से बता दो सुनो. If this is entropy, this should, because you have added, equated. If this is entropy, for example, ये zero है समझो. For a reversible process, this is zero. So when this is zero, this has the unit of entropy. So this should also have the unit of entropy. So all should have same units of entropy. So all terms must be मतलब सबके लिए entropy का term use करना है. This we call it as entropy change. Today we are going to see what is entropy transfer, what is entropy change, all those will be seen. This is entropy change. Okay, now this is entropy change. Please note down that this is entropy generation or entropy production. This is entropy change or entropy generation. Now, let us see what is this. Okay, let us see what is this. My dear students, this term comes only when there is a heat transfer. This term comes only when there is a heat transfer. Let us take adiabatic process. In an adiabatic process, this term is zero. But in non-adiabatic process, whenever there is a heat transfer, this term will be there. I repeat, my dear students, whenever there is a heat transfer, when Q is not zero, there will be heat transfer. Whenever there is a heat transfer, this term will be there. This term is associated with heat transfer. But everyone knows iska unit is same. This should have a unit of entropy. This is entropy. This is also entropy. This is also entropy. Unit की बात कर रहे हैं. But this is associated with heat transfer. That's why it is known as this total term, this d dash q by t is known as entropy transfer. That's why it is known as entropy transfer. That's why it is known as entropy transfer. So all of you listen carefully. The entropy change is equal to entropy transfer plus entropy generation. The entropy change is equal to entropy transfer and entropy generation. I repeat, my dear students, the change in entropy is due to entropy change is due to entropy transfer plus entropy generation. all of you listen carefully. There will be entropy transfer due to heat transfer. There is nothing like entropy transfer due to work transfer. देखो यहाँ पे entropy transfer is due to heat transfer. Entropy transfer is due to heat transfer. Now let us take adiabatic process. Let us take adiabatic process. In adiabatic process, what is the heat transfer? Zero. When this is zero, entropy transfer is zero. In which process the entropy transfer is zero? In which process the entropy transfer is zero? Adiabatic process. So in adiabatic process, the entropy, this heat transfer is zero. तो ये term zero हो जाएगा. So in adiabatic process, the change in entropy is only due to entropy generation, and that entropy generation will come only due to irreversibilities. That will come only due to irreversibilities. So therefore, in adiabatic process, I repeat, अब बहुत अच्छे concepts आने वाले हैं. So please be careful for about 10-15 minutes. In adiabatic process, there is no heat transfer. This will be zero. So entropy transfer is zero in adiabatic. So in adiabatic process, the change in entropy is only due to entropy generation, and that generation will occur only due to what? Irreversibilities. In a reversible process, entropy generation is obviously zero. Next, let us take reversible process. Reversible. In reversible process, there is no generation. In reversible process, there is no generation. There is no generation. In reversible process, there is no generation. So whatever the entropy change is taking place, it is purely due to entropy transfer. In a reversible process, the entropy change is due to entropy transfer only. Let us take reversible adiabatic. If it is reversible, generation is zero, because this term is coming only due to irreversibilities. In reversible process, entropy generation is zero. If it is adiabatic, heat transfer is zero, entropy transfer is zero. In a reversible adiabatic process, the entropy, see, there are multi-select questions, MSQ in GATE. That multi-select question can come something like this. Look at, what is that? In a reversible adiabatic process, first statement, देखो एक बार, in a reversible adiabatic process, first statement, entropy generation is positive. He gives statement like this. We have to select correct or galat. In a reversible adiabatic process, first statement, entropy generation is not zero and it is positive. Second statement, in reversible adiabatic process, entropy transfer is not zero. Third, in reversible adiabatic process, entropy change is zero. See, you have to be very, very careful. In reversible adiabatic process, when it is reversible, generation will be zero. The first statement is wrong. In adiabatic process, entropy transfer is zero. That is also wrong. He says it is not zero bola hai. And in reversible adiabatic, when this is zero, change in entropy will also be zero. That's why reversible adiabatic is no change in entropy, isentropic process. All of you, have you followed? Is it clear, my dear students? Very, very important. Very, very important. Very, very important. See, Mr. Vinash Kumari, I am talking only for reservoir. So when I am talking about the universe, it will be positive. When I am talking about the universe, universe means system plus surroundings. Universe means system plus, I am talking only about the system. There is a change in entropy. So no, ds is q by t. Yes, there is a change in entropy. There is a change in entropy. I never said the change in entropy is zero for reservoir. There is a change. You have a value of q by t, na? So there is Q, there is T, there is a change in entropy. Definitely, I never said the total is reversible. No, I applied only for reservoir. But you should not take, see, according to thermodynamics, when are you calling a process as reversible or irreversible? Dekho ek second. So you know very well, when the entropy change of universe is greater than 0, it will be irreversible. But you have calculated only for system. Now you calculate for surroundings. Then you add, you will get greater than 0. I'll be doing some questions on this now. Don't worry. Okay? Chalo. Where are we? Where are we? Arya, I was talking about this. Yeah. Okay. Now let us say this. ds is equal to d dash q by t plus del s generation. Please hold on. This is entropy change. Or change in entropy. This is entropy change or change in entropy. And this is entropy transfer and this is entropy generation. This is entropy change. This is entropy transfer and this is entropy generation. No problem at all. No problem at all. No problem at all. Look at carefully. Look at carefully. Now, understand carefully. You know, for reversible it is 0. For adiabatic this is 0. So the entropy change is occurring due to two reasons. Heat transfer. This is occurring due to heat transfer. Heat transfer is a boundary phenomenon. Heat transfer is a boundary phenomenon. I repeat, heat transfer is a boundary phenomenon. You know very well, whenever there is a heat transfer, I repeat, whenever there is a heat transfer, either it is transferred from the system or it is transferred from the system or it is transferred to the system. Look at carefully. Either it is transferred from the system or to the system. Means whenever there is a heat transfer, system says surrounding or surrounding says system. Means my system is interacting externally. What is the meaning of that? Say this is our system and these are surroundings. Whenever there is a heat transfer, it may be either way. Whenever there is a heat transfer, these are external. These surroundings are external. So whenever there is a heat transfer, it is an external interaction. What do you mean by external? जब सिस्टम दे रहा है वो अंदर अंदर नहीं दे रहा है, बाहर दे रहा है, या फिर सिस्टम ले रहा है बाहर से ले रहा है. Means system is interacting externally. That's why we call this heat transfer as external interaction. We call this heat transfer as external interaction. We call it as external interaction. We call it as external interaction. We call it as external interactions. And these irreversibilities may be friction, may be viscosity, may be lack of equilibrium. It is inside the system. So why this generation is coming? Can anyone tell why this generation is coming? It is due to irreversibilities. Where are those irreversibilities? Inside the system. Externally is already taken care. Externally is already taken care. Now these irreversibilities. So maybe friction inside, maybe viscosity, maybe lack of equilibrium. So these are known as internal irreversibilities. internal irreversibilities. So always remember the entropy change is due to two reasons. The entropy change is due to two reasons. Yeah. Okay. This is internal error. See, actually generation, it is a composite thing. That means don't think that surrounding, it is influencing. Surroundings are influencing. System is influencing. It is composite. I cannot say individually. It is influencing. Chalo, dekhte hai. Now, so always remember, my dear students, एक second. Always remember, the entropy change is due to two reasons: external interactions and internal irreversibilities. External entropy change is always due to two reasons: external interactions, internal irreversibilities. External interactions, internal irreversibilities. Absolutely fine. No problem at all. Absolutely fine. The entropy change is due to external interactions, internal irreversibilities. No problem at all. No problem at all. अब देखते हैं, all of you, listen. Now, let us take, and one more thing you try to understand. Please observe. Let us take system. Yeah. Now, these external interactions, they have effect. मैं फिर से बोल रहा हूं, सुनो. Internal irreversibilities that will affect system. Of course, surroundings are influencing, but internal irreversibilities that will affect system. Internally जो भी हो रहा है, that is affecting system. Internally it is occurring. And external, everyone knows when system is losing, for example, system is losing 200 units of heat, तो system के लिए क्या होगा? -200. Surroundings के लिए क्या होगा? +200. Means whenever there is external interaction, it is influencing both. So this external interaction has an effect both on system and surroundings. I repeat, my dear students. Internal irreversibilities, they deal with internally with system. External interaction means it will affect both system and surroundings. External interaction, अरे यार मैं बता रहा हूं, एक्सटेंड, जब मैं पैसे दे रहा हूं आपको, तो it will affect both. कैसे? When I am giving, it will be negative for me, and when you are taking, it will be positive for you. So it is affecting both. Whenever there is external interaction, heat transfer, देखो external interaction, यहाँ किसकी बात कर रहे हैं हम? Heat transfer, external interaction. So it will affect both system and surroundings. It will affect both system and surroundings. It will affect both system. इसका मतलब, if I write system, entropy change of system, entropy change of surroundings. Listen carefully. If I write system, सुनो ध्यान से. The entropy change of system is taking place due to, यहां पे भी system है where there is external interaction, यहां पे भी system है where there is internal irreversibility. Means system entropy can change due to external interactions and internal irreversibilities. System entropy can change due to external interactions and internal irreversibilities. But surroundings, देखो यहां पे कोई सराउंडिंग्स नहीं, इंटरनल इरिवर्सिबिलिटीज कोई सराउंडिंग्स नहीं है, बट यहां पे क्या है? देखो एक्सटर्नल इंटरेक्शंस, सराउंडिंग्स. So therefore, the surrounding entropy can change due to external interaction. I repeat, my dear students, the entropy change of system is यहां पे internal irreversibilities. Internal का मतलब क्या है? System. External means what? Both system and, अरे यार, internal मतलब अंदर ही. External का मतलब क्या है? System and surrounding दोनों में इफेक्ट हो रहा है. जब heat transfer हो रहा है, is it not affecting system? Is it not affecting surroundings? Yes. So that's why the external interactions, they have influence both on system and surroundings. इंटरनल इरिवर्सिबल ओनली सिस्टम, मतलब अगर टोटल ये सिस्टम का लिए एंट्रोपी चेंज ऑफ सिस्टम एंट्रोपी चेंज is occurring due to internal irreversibilities. System entropy change is occurring due to external interactions. मतलब सिस्टम का एंट्रोपी चेंज इंटरनल के कारण भी हो रहा है, सराउंडिंग्स के कारण भी हो रहा है, एक्सटर्नल इंटरेक्शन. बट फॉर सराउंडिंग्स देयर इज नो सिस्टम, देयर इज नो सराउंडिंग्स हियर. फॉर सराउंडिंग्स इट इज ओनली एक्सटर्नल इंटरेक्शंस. फॉर सराउंडिंग्स इट इज ओनली एक्सटर्नल इंटरेक्शंस. For surroundings, it is only external interaction, external interaction, external interaction. Now, let us take an adiabatic process. Let us take an adiabatic process. And you know, my dear students, in an adiabatic process, external interactions are zero. In adiabatic process, there is no heat transfer. So when there is no heat transfer, there is no external interaction. So external interaction का term zero हो जाएगा. कहाँ पे zero हो जाएगा? In which process the external term will become zero? It is in adiabatic process. It is in adiabatic process. I repeat, my dear students, let us take adiabatic process. In adiabatic process, external interaction is zero. In adiabatic process, the external interaction is zero. In adiabatic process, external interaction is zero. इसका मतलब adiabatic process में external interaction zero होगा. External interaction zero होगा. Means when surrounding entropy change is influenced by external interactions. But in adiabatic process, heat transfer is zero, external interaction is zero. Means surrounding में जो भी entropy change external के कारण हो रहा था, but in adiabatic process there is no external interaction. That's why there is no entropy change for surroundings. In which process the surrounding entropy change is zero? I repeat, my dear students. System entropy is changing due to external interaction and internal irreversibilities. Surrounding entropy change is taking place due to external interactions. But in adiabatic process, there is no heat transfer. External interaction is zero. When external interaction is zero, means surrounding entropy change is zero. This is the beautiful sentence, my dear students. In an adiabatic process, the surrounding entropy change is always zero. In an adiabatic process, the surrounding entropy change is always zero. And in adiabatic process, the system entropy will change only due to irreversibilities. If in adiabatic process, surrounding entropy change is zero, the system entropy will change only due to irreversibilities. But if that adiabatic is reversible, this will also be zero. So reversible adiabatic, no change in entropy of system. That's why it is isentropic. So the golden sentence that I am giving now is, this is one of the important statements, and please keep it in box. Please keep it in box. In an adiabatic process, as the external interaction is zero, the surrounding entropy change is zero. And this is one of the important equations for adiabatic process. In an adiabatic process, external interaction is zero, so the surrounding entropy change is zero, and the system entropy is changing only due to internal irreversibilities, only due to. This is one of the important conclusions in my entropy. Please इस पे थोड़ा ध्यान दीजिए. In which process the surrounding entropy change is zero? In which process the surrounding entropy change is zero? Very, very important. Very, very important. बोलो. Come on. हो गया? Yeah, that is the most important conclusion in an adiabatic process. I repeat, in an adiabatic process, I repeat, in an adiabatic process, the surrounding entropy change is zero. In an adiabatic process, the surrounding entropy change is 0, 0, 0. Okay ना? चलो चलो चलो, थैंक यू. चलो आगे बढ़ते हैं. So ये बहुत बहुत इंपॉर्टेंट है. ये बहुत बहुत इंपॉर्टेंट है. This is very very important, very very important. Now, let's proceed, my dear students. मैं आपको और कुछ देना चाह रहा हूं. Very very important, very very important. See, please understand carefully. Surroundings influence, but changes are taking place in the system. How surroundings are influencing? Due to heat transfer. Due to heat transfer, it will influence. Okay, na? Chalo. Now, let us take irreversibilities are associated with within the system. क्योंकि ये अंदर से friction है. So whatever external is there, heat transfer, वो तो already we have taken care. Already we have taken care. Now, let us take a system. And these are surroundings. Let us take a system, and can we call this complete as, एक second. Can we call this complete as, एक second. Can we call this as universe? Can we call this as universe? देखो, yes, अब देखो. Let us see universe. Already I told you that universe is an example of isolated system. Already we have seen universe as an example of isolated system. Already have seen universe as an example of isolated system. Already we have seen universe as an example of isolated system. Okay, please listen carefully. Universe is an example of isolated system, and in an isolated system there is no heat transfer, there is no work transfer, and there is no mass transfer. Okay, let us try to write the equation. ds is equal to d dash q by t plus del s generation. Listen carefully. Let us try to write this equation. Let us try to write this equation. ds is equal to d dash q by t plus del s generation. Okay, now let me apply this for universe. Let me apply this for universe. I am applying for suno. I am applying for universe. So let me apply this for universe. And everyone knows for universe, which is an isolated system. Dekho, system surroundings, if I take total, whatever is occurring, it is occurring in between only. If I take universe, यहां से कोई हीट ट्रांसफर नहीं हो रहा है, यहां से कोई, because whatever is occurring, it is between system surroundings. From the universe boundary, no heat transfer is taking place. So if I apply for universe में क्या क्या आ रहा है? System and surroundings. So heat transfer is zero. Heat transfer is zero for universe. Why? Because universe is an example of isolated system. Heat transfer is zero. 0 by t, 0 plus this is del s generation. And please note down that I can write universe is nothing but system plus surroundings. universe is nothing but system plus surroundings. So entropy universe is system plus surroundings. Universe is system plus surroundings, and that is entropy generation. And this is very very important. ये बहुत important है. Whenever he is asking you to calculate entropy production or entropy generation, I repeat, my dear students, whenever he is asking you to calculate entropy production or entropy generation, just to calculate universe entropy change. But how do I calculate universe entropy change? Calculate entropy change of system, calculate entropy change of surroundings, add, that will give me the entropy change of universe, which is nothing but entropy generation. And this is very very important. This is very very important. This is very very important, my dear students. Come on, come on, come on. Is it okay? Is it okay? Very good, very good. Awesome, awesome. Thoda recollect karo, because so many concepts are loaded. So many concepts are loaded. But things are occurring very sequentially. So many concepts are loaded. Of course, we have loaded it very gradually, not sudden. Come on, come on. Okay, na? Is it okay? Chalo. Now, I am going to give you one more important concept. Siddharth Bhopat Rao. Siddharth Baba. Babu Siddhartho. Come on, come on. Chalo, chalo, chalo. Are universe, is it occurring? Please be careful. Universe, and you know, why should I take universe is system plus F? Because irreversibilities are taking place during the process. When irreversibilities are there, how can I neglect? क्या कोई problem हो रहा है, or is everything fine? 1-2 students left. Let me check. Is everything fine? Dipole. Yes, yes, you can. Dipole. Is everything fine or कोई दिक्कत हो रहा है? 1-2 students left. Yeah, correct. कोई दिक्कत नहीं. चले? We'll start. Siddharth Bhopat Rao. Now, we'll be dealing with open systems. But before we deal with open systems, एक दो questions कर लेंगे. We'll be dealing with open systems. थोड़ा stuck हो रहा है. Yes, yes, yes. थोड़ा. अभी तो नहीं ना? Now it's fine ना? थोड़ा. Yeah, it will be there. एक सेकंड में चेक कर लेता हूं. अपने एंड से कोई दिक्कत है क्या? No. It's fine. Okay, chalo. Okay, tomorrow we'll be seeing entropy change for open system. Open system. आज तक जो डिस्कस किए closed system. Okay, okay, okay. But I'll take up some questions. Please, let me take up some questions. I will take up some questions. Entropy. एक second. I will take up some questions. Yeah. Let me take up some questions. Yeah. Let me take up some questions. एक्चुअली मुझे कंप्यूटर का कोई आता ही नहीं था, आप तो हंसते थे, यू मे बी लॉफिंग एट मी कि मैं मेल भेजना या मेल आईडी क्रिएट करना कब आया था पता है? व्हेन आई वाज इन इंजीनियरिंग कंप्लीट होने के बाद तब मेल आईडी था। स्टकअप हो रहा है, बीच में थोड़ा स्टकअप हो रहा है। हाँ, कोई दिक्कत नहीं, विल कंटिन्यू। एक सेकेंड। या okay, yes, let's proceed. The equation ds is equal to d dash q by t, everyone knows. Stuck up हो रहा है ना? अच्छा, मोबाइल पे देख लेना, ठीक आ रहा है। Yes, this equation is valid only for reversible process. याद है आपको? What is the answer? It is valid only for reversible. It is valid only for reversible. Okay na? Chalo. Now let's take the next question. Read the question and try to answer. 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 A system is changed from a single initial equilibrium state to the same final equilibrium state by two different processes. See, let this be entropy, let this be temperature. Now, there is one process, there is another process, right? Now, देखो दोनों के लिए सेम स्टार्टिंग पॉइंट, सेम एंड पॉइंट. Which of the following is true? Whenever the initial and final points are same, when end points are same, what will be the entropy change for both? Everyone knows entropy depends only on endpoints. Therefore, now entropy change for reversible is equal to entropy change for irreversible. So therefore, the answer is A. Therefore, the answer is A. Is it clear, my dear students? Is it clear? Is it clear? Now, so look at the question. A system is changed from single initial equilibrium state to a same final equilibrium state. But the reversible or irreversible, same initial state to same final state. So when endpoints are same, whether it is reversible or irreversible, it will be absolutely same. It will be absolutely same. No problem at all. Okay. Now we'll move to the next question. Read the question. Please read the third question. Read the third question. So we'll do one thing. So we'll continue tomorrow. So we'll stop here. I'm stopping the class. I'm stopping the class. We'll stop here. थोड़ा stuck up हो रहा ना? नहीं? Not a problem, I suppose. We'll stop for today because we have learned so many concepts. We'll be starting from third question. Don't worry. We are stopping the class. Okay? Okay? Chalo, bye bye. I'm stopping the class. Tomorrow we'll meet. Okay? Thank you. Please revise all the concepts. Tomorrow I'll take up this question. Then we'll discuss entropy change for open system also. Okay? Chalo, stop.